very end. Integration by parts. And roughly speaking, integration by parts is a technique that you're going to use when you have an integral of a product of two functions, similar to the product rule. And remember our derivation from yesterday. Just recall the beginning and the end of it. We ended up getting, you have two functions, u and v, that the integral of u dv is equal to uv minus the integral of v du. This is what we'll call the integration by parts formula. Okay, now, when I write dv here, your first inclination is just think, oh, that's the d at the end of any integration. Okay, but usually this dv looks like some function times dx. And over here, this du is some function times dx. So what you really have is u times some function times dx, and over here, v times some function times dx. Just so happens that that function times dx is the derivative of whatever your function u is. Okay, so let's do an example, because this is all just, I don't know what that means. Okay, so let's see, what's my first example? And today is almost going to be exclusively examples. So let's look at x times e to the x dx. Okay, we want to find the integral of this, right? Now, if you were guessing, already you can see this is going to be hard. A function whose derivative is x times e to the x. You just think about it for a second. Let's just ponder. Nope, not sure what it should be. All right, but let's do the following. Let's try to take this equation and put it into this form. And if we put it into that form, then we know by the formula we can rewrite it in this form, and we'll get a new integral. Now, that doesn't seem like it's any better, because you still have to integrate. But maybe the new integral is easier. Okay, so let's just experiment. Just see if this formula is worth a darn. So let's try it like this. Let's make this the u, and this part the dv. Remember I said the dv is going to be a function times dx. So, and usually the way I'll write this is u equals x, and dv equals e to the x dx. We'll just put this on the side, this nice little side work. Okay, now, if I do that, then I know I can rewrite my formula as u times v minus the integral of v times du. Okay, but to do that, I need to know what v is, and I need to know what du is. Okay, so let's see. Well, we got u here. U is x. By definition, what is du?
Derivative.
All right, it's the derivative of u times dx. Okay, so what's the derivative of u?
1.
1. Okay, so this is just dx. Right, 1 times dx, if you like. And on the other side, I'm looking for v. So I know that dv is e to the x dx. So what I need, right, is an antiderivative for e to the x, right? How can I get v? Well, if I integrate both sides, I'll get v on the left. And on the right, I get an antiderivative for e to the x.
Yes.
E to the x, sure. Okay, now you may say, well, I'm missing something, right?
Yeah, plus
C, right? Okay. What's going on in this method is I can take any antiderivative in here that I want. I can put e to the x, I can put e to the x plus 4, I can put e to the x minus pi, anything I want, okay, into this method. So, I take the easiest one. And the easiest one is plus 0. All right, so I used my u and dv to give me a du and a v. And now by the integration by parts formula, the integral of u dv is u times v. Okay, so let's see, x times e to the x minus the integral of v, which is e to the x, du. But du is just dx. Right? Let's get dx. And lo and behold, I've replaced my very difficult, we don't have a clue how to do it integral, right, with a longer expression which contains an integral that we definitely know how to do. Right? So now write this as x e to the x minus, and what's the integral of e to the x?
Yeah.
E to the x
Plus C.
plus c. Okay, at the very end of the day, of course, we better have this constant of integration. Okay, so, and, well, okay, I'd probably factor this. I think this e to the x times x minus 1 plus c. Don't worry about that. It's just, I'm just anal. Can't help myself. By the way, anybody know the joke about the waitress and e to the x?
No.
No? Well, okay, so there's two mathematicians, they're in a bar, and they're arguing about whether or not people know math, in America today. And one of them says, no, people are just horrible, they don't know anything. The other one says, no, I really think people are getting it more these days. So the one who thinks we know nothing, he goes to the bathroom. And while he's gone, the other guy, he sits there and calls over the waitress. He says, look, in a second I'm going to call you over, okay? And I'm going to ask you some questions. No matter what I say, whatever I ask you, you just say e to the x. So the other guy comes back from the bathroom and he says, hey, why don't we do a little test? I'm going to call over somebody just randomly, and we'll ask them some math questions. The guy says, oh, well, that's fair. So he calls over the waitress and says, excuse me, ma'am, could you tell me, what's the derivative of e to the x? And she says, e to the x. And he says, now, what is the integral of e to the x? And she says, e to the x plus c. Okay. So that's math humor for you. Okay. Any questions on how we work this? No? Okay, let's try another one. Let's make it harder. And we're going to do the integral of x squared times e to the x dx. So again, we have a product of functions. So we think, yeah, can I do this with just thinking about it? No, that looks pretty hard. Okay, so I won't do that. So why don't we try integration by parts? So what should be our u and what should be our dv?
U is x squared.
Uh-huh.
And dv, which is e to the minus x dx.
That's right. That'll be our u, that'll be our dv. Okay, looks good. So let's see, let's write that. U equals x squared. dv equals e to the minus x dx. So du, well, it's the derivative of u times dx.
2x dx.
2x dx. Okay. You agree, Shirley?
No.
Okay, good. Okay, and what's v going to be? Well, it should be an antiderivative of e to the minus x. So we need a function whose derivative is e to the minus x. Negative e to the, what should be? Should be to the x or to the negative x?
Negative x.
To the negative x. All right, let's see, let's check. If I take the derivative, okay, derivative of e to the minus x is minus e to the minus x. So if I throw another minus in there, I get positive e to the minus x. That's what I want. Okay. Cool. So now I can put down uv, which is x squared times minus e to the minus x. So minus x squared e to the minus x. Minus the integral of v du. So v is minus e to the minus x. Well, I'll just pull the minus out front. So I'll do that in the next step. So minus e to the minus x times du is times 2x dx. Okay, so let's simplify this integral a little bit. I have a minus and I have a 2, so I can pull those out front. So this becomes minus x squared e to the minus x, and then the minus 2 comes out and gets plus 2, integral of, well, x e to the minus x. Oh dear. Well, we still don't know how to do it. But it's somehow easier, right? Because instead of having an x squared, we have an x to the first. So, let's try it again. Right? And if it works like this one did, right, then we'll just get an e to the minus x in the end. Okay. So let's just do this as a separate problem. You have integral of x e to the minus x dx. What's going to be my u? X. And my dv? Okay, so u equals x, dv equals e to the negative x dx. So du
dx
is 1 times dx, or dx. And v, no, we already solved this problem. It's just minus e to the minus x. Okay, so this integral by the integration by parts formula becomes uv, so minus x e to the minus x, minus the integral of v du, so minus e to the minus x dx. Okay, I have a minus, which I can pull out, make that into a plus. Okay, and we got exactly what we'd hoped for. We've reduced this problem to now an integral, which is just e to the minus x. Okay, so we get minus x e to the minus x. And what is the integral of e to the minus x? It's actually the same thing we've done over here. Minus e to the minus x. E to the minus x, and of course, plus c. Good. So now we can take this, which remember, this came from this integral, which we pulled out of here. Okay, so we have to plug it all back in. This becomes minus x squared e to the minus x plus 2 times, okay, now this integral evaluated to this. Minus x e to the minus x minus e to the minus x plus c. And just take this, shove it. And, well, okay, I would probably want to mess with this. Okay, you have an e to the minus x, and e to the minus x, and e to the minus x, which is out, and then you're left with a minus x squared, and a minus 2x, and a minus 2. Let's see, you could even pull out a minus sign if you wanted to make these all positive. Okay, now, time permitting, at the end of the day, I will show you a nice trick to simplify this process. Because somehow, what would happen if this was an x cubed? What do you think? Right. What would happen? Right? Then the next step, it would be an x squared, and then it would be an x, and then it would go back to e to the minus x, right? Okay, so I'll show you just a nice little way to kind of simplify the pattern so that you don't need to do all this work. Bless you. Okay, all right, let's see, what's another one? Okay, here's an unexpected one. This one is a bit unexpected. Okay, let's remember, what is that?
Limits.
Yes. C, of course, as our waitress tells us. This is why you don't forget to tip your waitress. Maybe she gives you a good tip too. So you integrate 1 over x and you get ln of x. differentiate ln of x, you get 1 over x. What if you integrate ln of x? Ooh. Where does that fit into this sorted game? When you think of a function whose derivative we figured out was ln of x, it's not clear. Well, it seems kind of trivial to use integration by parts here because there's not, you don't think of there being two functions to multiply, right? It's just the one, but just for shits and giggles, let's give it a shot. What would you make if you had to do integration by parts? By the way, let me leave that formula up here so we have it. What would you call your u and what your dv?
U, Linux.
Sure. And dv?
DX.
dx. No, not so many choices. Right?
Yep.
Okay, so u equals ln of x, and dv equals dx. So what would be your du?
1 over x.
1 over x. That's good, right? The nice thing about integration by parts is you can take part of your function that you don't know how to integrate and forget about it. Just say, oh, I only need to differentiate it. Right? So I'll differentiate ln of x. That I know how to do. So we get 1 over x dx. Okay, and then if dv is dx, what is v?
X.
Well, dv equals dx and integrate.
Yes.
V equals
X.
x. Okay, let's see what we get. So we put in uv. Okay, so that's x ln of x minus integral of v, which is x du. So x times 1 over x dx. Okay, we'll see. That's x ln of x minus, okay, x times 1 over x. Oh, that's nice.
X over x. 1.
Okay, so you just get integral dx, which is just x. So we get x ln of x minus x, of course, plus c. Okay, now that seems too easy. Let's make sure this is right. Okay, let's just check. Let's look at the derivative of x ln of x minus x. Okay, I don't need the plus c because I know the derivative of the c will be 0. All right, so I have to use the product rule on this guy. So let's see, I do say the derivative of the first times the second. So that's 1 times ln of x plus, okay, now I hold the first one and do the derivative of the second.
1 over x.
1 over x. Okay, that's nice. Okay, then I do minus the derivative of x, which is 1. Okay, so let's see. X times 1 over x is 1. Minus 1 is 0. So I just get ln of x. It works. Sweet. So this is clever, right? This is not how you'd expect to be using this. Okay. Let me ask you guys to find an error in proof. I always think these are fun exercises. You know, I think I'm going to save this one for the homework. I'll put it on a homework. It's a good one, but I want you guys to think about it. So I'll save it for a moment. Okay, so let's do, okay, so here's another example. And this one is another clever use of it. Because in this example, we're never actually going to simplify the integral. It's never going to become something that we know how to integrate. Right? So this is very peculiar. So I'm gonna do something here which at the beginning it won't seem apparent why. I'm just gonna give this a name. Whatever the value of this is, I'm gonna call it I. Okay, so I actually do have a product of functions here, right? Sine of x times sine of x. Yeah, it's sine squared, but that's still a product of functions. Can you think of a nice way to break this up? I could rewrite this. Okay, so Dina's saying we have sine squared of x plus cosine of squared x equals 1. And so you could write sine squared as 1 minus cosine squared. And this is a useful observation. But right now it doesn't help us a whole lot only because we don't know how to integrate cosine squared. Okay. So how could we just split this up? Just in the way we do integration by parts. Just looking at the functions we have. I mean, we have a few options. We could make u to be all of sine squared and dv to be dx. Okay, let's try that. Let's see what happens. So du is going to be what?
It's going to be 2 sine x, cosine x.
2 sine of x, cosine of x. Very good. Times
Dx.
Times dx. Okay, and what about v? If dv is dx, then v equals
1
x. Okay, so let's see what would happen. We would then get uv, so x sine squared x, minus the integral of v, which is x du. You get 2x sine of x cosine of x dx. All right. Now, one observation you make is that 2 sine of x cosine of x is actually sine of 2x. So I could rewrite this bit as x times sine of 2x. And unfortunately, this has made the problem somehow worse because we don't know an antiderivative for x times sine of 2x. Now we probably have a chance at using integration by parts again on this, but who knows where it's going to go. You'll probably just end up with cosine of 2x back where you started, so this is dangerous, right? Okay. So it's not clear where it's going. So let's try a different approach. Well, instead of making u all of sine of x, what if we just made it one of them? All right, and then threw the other side of x into the dv. So this really is, right? U dv is sine squared dx. So du is
Cosine x dx.
cosine of x dx. Excellent. Okay. And what about v?
We're going to use
Negative cosine. That's right. The antiderivative of sine of x is negative cosine. Okay, so let's see what we get now. uv is going to be negative sine of x cosine of x minus the integral of v du. So that's negative cosine squared. Negative will come out front. I get cosine squared x dx.
plus c there. Plus c.
Well, we're integrating it, so the plus c. You mean here?
Yeah.
Well, remember, whenever we do this process, we can choose any antiderivative for
Oh,
v.
like 0.
So I choose the one with a 0. Okay, now, it seems like we've really got ourselves back into a completely different pickle. In fact, it seems like the same pickle that I warned Dina about, right? Okay? We've just ended up with another integral that we don't know. But let's use Dina's observation. cosine squared is 1 minus sine squared. So let me rewrite this. Okay, minus sine of x cosine of x plus the integral of 1 minus sine squared. Now, why is this helpful? We somehow reduce ourselves to the integral that we didn't know to begin with. Let's keep going with this a little bit. Okay, so first, I can break up an integral over a sum or a difference. So this is the integral of 1 dx, which is dx, minus the integral of sine squared of x dx. Okay, so this one we know how to do. That's a good one. Minus sine of x, cosine of x. Okay, plus, well, the integral of dx is just x. I won't add the plus c for the moment because it'll, well, actually, I don't want to evaluate that anyway. Okay, and then I have to do minus the integral that we want anyway. And then we gave that integral a name in the very beginning for an unknown reason. Well, this is the reason, so that we can replace that long expression with just I. Okay, so I equals blah, blah, blah minus I. Okay, well, I don't like having i's on both sides, so let me put them all on one side. So if I add I to both sides, then I know that 2 i's better than 1. 2 i's is minus sine of x cosine of x plus x plus c. But I don't want 2i, I want I. That's what I was looking for, so I divide by 2. And I get I equals a half minus sine of x cosine of x plus x. All right, and then of course the half hits the plus c, but it's just a constant. Stays plus c. Okay, what's next?
Next. Plug I.
Wait a second. I, that, geez, that's what we wanted. Wait a second, we have. That's what we wanted. So somehow we were able to compute I through the back door. Yeah, we fiddled around with these things, changing the form, and then somehow in the end the answer pops out, even though we never had to evaluate any of the hard integrals. Isn't that sweet? Incidentally, it's very easy to do cosine squared now without even doing this trick, right? If you want to know cosine squared, we use Dina's trick. And now, this is just x minus the integral of sine squared x, and we already know it. It's just as I. Well, I won't write the whole thing. Let's write I again. So it's just x minus I. But now, if you do x minus I, it's actually just going to change the sign of these things because of the minus. And then you have an x in there. So here you have a half of an x. But you subtract half an x, so you end up with just half an x. So you'll actually end up with a half sine of x cosine of x. You lose the minus. And plus, yeah, plus x. Plus a half x. Let's see. So the integral of cosine squared is almost the same. So that's not bad. All right. So here comes the more general question. If you have a product of functions, which should be your u and which should be your dv? We already saw that if we chose poorly, you know, maybe you don't simplify things. And let me give you another example of choosing poorly, and seeing how that can really make your life difficult. Let's again try this derivative, or this integral. Okay. We saw that the correct choice was to make x equal to u and e to the x dx be dv. Well, let's say we made the incorrect choice. We went u equals e to the x, and dv was x times dx. Let's see, so du, well, that's nice and easy. E to the x dx. And what about v? 1/2 x squared. Okay. So we get uv, so 1/2 x squared e to the x, minus the integral of v du. So we can pull the half out, x squared e to the x dx. Is it true? Yeah, absolutely. Is it helpful? Definitely not. We've made the problem worse, right? We've increased the exponent, not decreased it. So this is what happens if you choose poorly. So the question is, how can you choose wisely? So here's the acronym, and I would really appreciate if somebody could come up with a better mnemonic for this. So this is just a general rule. It's not always going to be true, but it's a good place to start. So L stands for logarithmic, I for inverse trig, right? You think an arc sine, arc cosine, these things. A for algebraic, okay, these are like polynomials. T for trig, and E for exponential. So roughly speaking, these are the 5 kinds of functions that you know about. Right? We have logs, inverse trig, algebraics, exponentials. Right? We don't know too many more. By the way, where would hyperbolic trig functions fall in this? Well, do you remember how hyperbolic trig functions were defined?
Oh, is 1/2 e to the x minus 1/2 e to the x?
Yeah, so like arc sine, sinh of x, right, was 1/2 e to the x minus e to the minus x. Okay, so it's actually just an exponential sort of function. So it wouldn't be a bad idea to start thinking, oh, maybe it's in the exponentials. Right? On the other hand, it's not just one exponential function, it's actually a combination of some. All right, so you might factor it. Factor out an e to the minus x, and then you get e to the 2x minus 1. You start playing around with it. Oh boy, this is really bad. A product of things. Yeah, so it's not so clear what's going on, right? Okay, so maybe you try one. You play around with it, see where you think it should fit. All right. So what is this supposed to mean? So whichever one is higher up on the list, that's the one you should choose as your u. Okay? So for instance here, you have x e to the x. X is an algebraic function. Polynomials are algebraic functions. Rational functions, right? Quotients of polynomials, that's algebraic. So that's algebraic, and e to the x is exponential. Since algebraic comes first, you let the x be your u. Right? Here you can see we didn't, and you got a bad result. So what if we had x ln of x? What should we use as our u? ln of x, right? ln of x is a logarithmic function, comes before algebraic. Okay, let's test it. So u equals ln of x, dv equals x dx. So du is 1 over x dx. V is equal to 1/2 x squared. Now at this point you might think, whoa, we just saw this happen, right? This 1/2 x squared business got us into a lot of trouble. Okay, well let's take a look. So this becomes uv, so 1/2 x squared ln of x minus the integral of v du. Ah, something nice is happening. When we multiply these, v du becomes a half x squared times 1 over x, which is just a half x. And of course, I pulled a half x. And this we can do. A half x squared ln of x minus, let's see, we get a half, and then the integral of x is another half x squared, so we get a fourth x squared. Okay, so this is a nice little rule. The way that I came up, the mnemonic I first heard for this was lions in Africa tackle elephants. I think we can do better.
I had a teacher, he just said I'm late, but we didn't have inverse trig functions in ours. So I before late.
I before late.
The I.
You mean you want me to move the I?
No. I don't know.
Come on, somebody. So you don't have to come up with an answer right now, but somebody come up with a better thing than lions in Africa tackle elephants. Lathe is a teacher's enigma. Okay, so somebody can do better. Okay. All right, I give you mucho bonus points if you come up with a good mnemonic, right? All right, let's do one more using this mnemonic to see if it helps. Somehow morally, if I write down x times e to the x, it makes sense to let the u be the x, because when you go through that process, right, it decreases the degree. Right? If you have an x squared, it becomes an x, and then the next time it goes away. Right? But what happens if neither of them is an x, right? Then it's not so clear what should happen. So for instance, what if we had e to the x times sine of x? Here, I mean, without any sort of guidelines, what do, right? You just test them both. But if we use this mnemonic, it says trigs come before exponentials. So we should let the trig function be our u. Okay. So then du is going to be what? Cosine of x, x, and v,
e to the x.
Okay? Okay, so let's plug this back in. It's u times v, good, e to the x sine of x, minus integral of v du, so e to the x cosine of x. Okay, now it seems like we've snookered ourselves, right? Because we've somehow ended up with another integral we don't know how to do. Okay, but let's use our memory, right? We already saw a case where you could somehow go from sines to cosines and then get sines back again. Now there you have a sine squared and a cosine squared, so it's very easy. But what if we applied this integration by parts formula again to this? What do you think is going to pop out again as your integral?
It's not sine x.
E to the x sine of x, right? Which is what we started wanting. So why don't we, I don't know, give this a name and take a peek and see what happens if we evaluate the integral of e to the x cosine of x. So we use the same idea. Cosine is u because it's the trig function. And du is now minus sine of x, dx. V is still e to the x. So this works out to be, let's see, uv to the x cosine of x minus the integral of v du. Ah, we get what we suspected we would get. Okay, except we get an extra minus out here, makes it into a plus. That plus is important. The reason why that plus is important is now when we plug it back in up here, it's going to turn into a minus. So when we add it around, we're going to get 2i instead of 0. Okay, so let's plug this in. This becomes, well, we keep the e to the x sine of x minus, it's e to the x cosine of x plus the integral we were looking for, which we called I. Okay, so this is actually minus e to the x cosine of x minus I, so I can add the I to the other side. And I get 2i equals, well, whatever is left over. I get e to the x and then the sine of x minus cosine of x. Divide by 2, voila. What we were looking for. Fine. You know, what's really cool is you look back at this and think, imagine if you were trying to guess the antiderivative. What chance in the world is there that you would guess that? Okay, so we have a few minutes left. I want to show you a neat little trick. I learned this from watching the movie Stand and Deliver. It's called the Tic-Tac-Toe Method.
Should we write C in this one?
What's that?
Should we write plus C?
Yeah, yes, for sure. Where would have been a good place to add it?
From the beginning.
We actually needed to add it
No, up.
up here. Let's see,
Yeah,
where did we,
yes.
did we evaluate an integral somewhere?
Yeah,
Let's see.
and then maybe.
Yeah, this is bad the way we've done this here. So I'm trying to think where would be a natural place to add it for the first time.
After I.
So here we evaluated this.
Then we go up.
We evaluated. Okay, well, we'll just put it somewhere in here. It really doesn't matter a whole lot because in the end it's just going to be, well, put it on the outside. Not so important, but you're right. Okay, so whenever you have a situation like this, say x cubed sine of x. So we have lines in Africa, tackle elephant. So the algebraic comes first, right? The trig comes second. So that would be the u. And what's going to happen when you do integration by parts? Well, it's going to spit out another thing just like this, only you'll probably have a cosine, and that'll become an x squared. And then you'll do it again, and it'll probably turn out to be a sine, and that'll turn out to be an x. And then you'll do it again, and that'll turn out to be a cosine, and that'll go away. So we actually can just put all this work into one little chart. We start with our du's on the left, and then our other function, which is, our u's on the left and the dv on the right. Okay, and we don't worry about the dx. Okay, the way we write this. And what we do is we just differentiate this algebraic function until it goes to 0. So 3x squared, 6x, 6, 0. Okay. Now, for as many times as we took derivatives, we're going to take antiderivatives on the right. So the antiderivative of sine of x is
Negative cosine.
negative cosine. And of negative cosine?
Negative sign.
Negative sign, and a negative sign,
Cosine.
cosine, and a cosine,
Negative cosine. Sine.
it's going to be
Sine.
sine, right? Derivative of sine is cosine. Okay, so we did it for as many. And now, everything I'm doing, you can see why it's happening just by looking at the integration by parts process. I'm going to draw some lines going down diagonally. And starting from the top line, I'm going to write a plus or a minus. Okay, and always start with a plus. Okay, and I'm just going to alternate. Plus, minus, plus, minus. Okay. And now here comes the answer. You just read these things along the lines. X cubed, and there's a plus, you can think of times a plus, right? Times negative cosine of x. So you get negative x cubed cosine of x. And the next one is, we get a negative negative becomes a positive. So 3x squared sine of x is positive sine. 3x squared sine of x. Okay, the next one is a positive and a positive, so it's still positive. 6x cosine of x. And then the last one, you have a negative and a positive is a negative, so minus 6 sine of x. And then, of course, plus. Now, all we've done, mind you, these minus pluses, right? These are coming out of the fact that the formula, right, has this uv minus the integral of v to u.
Can we go back to this? Can we go back to what you have done?
Can we go back to it?
Yeah. What you just said about.
Okay, so I'm not.
How did you write this as a?
Oh, okay. How did I get there from here?
Yeah.
Okay, so first you're always going to read along the lines. Okay. First thing you do is find the sign, right? And the sign is always going to come from, well, you have a sign here, you have a sign here, and you have a sign here. Positive, positive, negative gives you a negative. Okay, because you're always multiplying. If you had like plus 1 times plus 1 times minus 1. Okay. Here you'd have positive, negative, negative.
Which is positive.
Positive. Here you have positive, positive, positive,
Positive.
positive, positive, negative, positive,
Negative.
negative. Right? So that's the first thing I can do. I can get the signs. Okay. And then to get the actual function, I just multiply x cubed and cosine of x. 3x squared sine of x. 6x cosine of x. 6 sine of x. And you'll see that's exactly what we get out.
Once you get the plus and minus, it's all the same.
Always start with a plus,
Plus, minus,
and then alternate. Plus, minus, always alternate. So earlier we did x squared e to the x, right? And remember, it took us two-part integration by parts. But if we do it like this, we can do it much faster. 2x to 0, e to the x, e to the x, e to the x. Okay. Oops, forgot one. Plus, minus, plus. Okay, so we get x squared e to the x, minus 2x e to the x, plus 2e to the x, plus. Yeah, very fast.
This rule is only for like power x.
Yeah, so this method is going to work best when you have a power of x, right, or some function, yeah, a polynomial function. Right? When both of these say are, say one is a trig and one's an exponential function, this whole method's not going to work because there's no stopping point, right? Okay, I'm actually thinking about a way you can add it into it, but it's going to take me a little time to keep working on it. Yeah. In any case, this is whenever you get these problems where you have some power of x times a trig or an exponential function, this is just a very slick way to attack these. When I took the AP Calculus exam, I remember they had one that was like x to the 4th e to the minus x. And it was on the multiple choice part, which is supposed to really slow you down, these kind of problems. And I just went, boom, move on. It's very nice. Simplified method. So, okay, so it's just a little fun trick. Any questions?
Thank you.